In this fifth and final video on the kinematic equations, we'll look at what makes them unique, and we'll look at how to decide which of the kinematic equations is right for you. So we have four kinematic equations. Vf equals I plus AT. Delta x equals 1/2 Vf plus Vi times T. We have delta x equals VIT plus 1/2 AT squared. And we have VF squared equals VI squared plus 2A delta x. So in all of these equations, delta x is displacement. T is time. A is acceleration. Vi is initial velocity or starting velocity. Vf is final velocity or ending velocity. The velocity you begin at, the velocity you end at. Those five variables are the only variables that are present in the kinematic equations. And if we look carefully at each of the kinematic equations, they're designed to eliminate one of those five variables. In the first one, I have Vf, Vi, A, and T. The only one that's missing there is delta x. This is the kind of equation that you would use if you did not know the displacement of your object. In the second one, we have delta x, Vf, Vi, and T. The one that's missing here is acceleration. This would be the equation that you could use if you did not know the acceleration of your object. Here we have delta x, Vi, T, and A. The one that's missing from this equation is Vf. So this would be your no Vf situation where you don't know the final velocity of your object. And this last one has Vf, Vi, A, and delta x. The variable that's missing from this one is time. So this would be the equation you could use if you did not know the time of motion. So again, we could describe this one up here as the no delta x equation, no displacement. So if you don't know the displacement of your object, but you have Vf, you have Vi, you have A, you have T, you have the other four variables, you can work with them. Again, this one here, the variable that's missing is acceleration. That is the no A equation. So again, if you know the displacements, the velocities, the times, you can work with that equation without knowing what the acceleration is. This one here is the no Vf. You don't know the final velocity. You don't have to have the final velocity to use that equation. And then this last one, again, no time. Now, I was asked the other day about if I'm going to give you that information on the test, tell you which one's the no delta x. No, I'm not going to give you that. You can look at the equation to see. Again, look at this equation. There's no delta x in it. That is the no delta x equation. That is the kind of equation you would use if you didn't have a displacement. And when you look at this equation, there's no A in it. That's the equation you go to when you don't know the acceleration of your object. More often than not, it's not even that stuff that we're focused on. More often than not, what we're actually focused on is finding the answer to a question, which might ask us, what is the final velocity? What is the displacement? What is the time? That kind of thing. And that's how we choose the equations that we're going to work with, not by what's missing from the equations, but most often we choose our equations based on what we're trying to find. A car slows from 25 meters per second to 10 meters per second. While covering a distance of 12 meters. is acceleration. So again, we start our process using that problem-solving process by figuring out what numbers we have to work with and what we're trying to find. So as far as numbers we have to work with, we have 25 meters per second, we have 10 meters per second. These are both velocities. This says from 25. From indicates VI, tells you where you start. 2 indicates final velocity, it's telling you where you end. If you went from my room to the office, from my room means you started at my room. To the office means you ended at the office. From 25 means you started at 25, that's VI. To 10 meters per second means you ended at meters per second, that's VI. And we know our displacement, our delta x, is 12 meters. There are no hidden numbers in there.
Shabria Edie, please report to the office. Shabria Edie, please report to the office.
What we're trying to find here is acceleration. We're trying to find A. So again, as we decide what kinematic equations to use, this is what's most important to us. I have VI, I have VF, I have delta x. And I'm trying to find an acceleration in this particular circumstance. So when I go back to all of my equations, that has an acceleration in it, so that equation could be used to find A. That has acceleration in it, so that equation can be used to find A. That has acceleration in it, so that can be used to find A. Typically, there's as many as 3 equations that you could use to find the variable that you're looking for. Real big exception, that's VI, which could be any of the equations. So I look at those 3 equations and I think about the information that I have. I can use this one, but I need VF, VI, and T. And when I look at the information I have, I don't have T here. To use this equation, I need delta x, I need VI, and I need T. I don't have T here. When I look at this equation, I need VF, I need VI, and I need delta x. When I look at the information I have VF, I have VI, I have delta x. So again, I'm not thinking about, oh, time's not here. I need the no time equation. I'm thinking about what I have and what I'm trying to find. I have VI, I have VF, I have delta x. I'm looking for A. I have VF, I have VI, I have delta x. I'm looking for A. So I'm going to use that equation. I'm going to use VF squared equals VI squared plus 2A delta x to solve my problem. My VF is 10 meters per second. This is 10 meters per second squared is equal to VI, that's 25 meters per second. Again, that number's got to be squared. Plus 2 times A. A is my variable. Times delta x, 12 meters. Whole lot of simplification that we have to do here. So my 10 squared, that's 100. That would be meters squared per second squared. Not only do we square the number, but we have to square the unit. 25 squared is 625. And again, that's going to be meters squared per second squared. So again, not only do we square the number, but we square the unit. 2 times 12 is 24 times A. First thing I'm going to do is subtract the 625 from both sides. So we can completely eliminate that over here. 24 meters times A equals negative 525 meters squared per second squared up here. And don't be worried about that negative sign. The object was slowing down, so we would expect a negative acceleration. And this negative sign is what's going to give us that negative acceleration. I'll wrap this up then by dividing by 24 meters. Those cancel, and I'm left with A equals 525 divided by 24 is 21.875, so 21.9. I'm just rounding arbitrarily again. I'm not using significant figures. That meter will cancel out one of those meters. So my unit is meters per second squared. Again, that's negative. We cover that negative sign. It's negative 21.9 meters per second squared. Could I have used any of the other equations up there to solve my problem? Absolutely. I can get acceleration from this equation, but I need time first. And I could ask myself, do I have a way of finding time? And absolutely, I could use the second equation to find time. I could handle this in a two-step problem. It comes down to what makes sense to you, what you see, what you feel comfortable with. And I have everything I need to find the time of this one by using that equation. Delta x equals 1/2 VF plus VI times t. But delta x is 12 meters. That's 1/2 VF plus VI, 10 plus 25 meters per second. So 35 meters per second times t. So I would go ahead and I would simplify what I have on the right-hand side. 0.5 times 35 is 17.5. Times t. Then I divide both sides by 17.5. Twelve divided by 17.5 is 0.6857. So I'm going to round that to 0.69. The meters squared cancel. The second moves up, so my unit is seconds. And I can add that now to the list of things I know. And now I have VI, VF, delta X, and T, which means now I'm free to use this equation to find A. VF equals VI plus AT. VF is 10. VI is 25. A is what I'm trying to find. And the time is 0.69 seconds. I'll subtract 25 from both sides first. This completely cancels out over here. And I end up with A times 0.69 seconds. And then over on this side, I end up with negative 15. Again, don't worry about the negative sign. It's slowing down. We need negative acceleration, and that's the number that's going to give it to us. And then we'll divide both sides by the 0.69 seconds to get A equals 15 divided by 0.69. 21.74 meters remains on top. It's seconds divided by seconds, so it's seconds squared on the bottom. So again, we have options here. We have a number of ways of coming up with the answer. We can do it in single-step problems. We can do it in multiple-step problems. It's whatever works for you. And whatever you see first, whatever you're most comfortable with.